Right. So good morning, all of you. So this is a SPARC webinar that we are conducting as a part of the SPARC project. And the webinar title today is called Hands-on Modeling and Simulation of Polydisperse Flows. Okay, so I'll talk in detail in the first session as to what polydisperse flows are and what sort of tools we'll be using to model it. But just a brief opening welcome that in this webinar, which will happen over the next 2 days, so we have 4 sessions in total. In these sessions, we'll talk about modeling as to how to model these polydisperse multiphase systems. We'll talk about FEM methods, particularly the Galerkin FEM methods, as to how to use them and solve these kind of complex modeling problems. And in these FEM methods, it's not just talk and theory. I'll give you hands-on. For those who are sitting here, will benefit especially from this. That I'll do things in front of you on these machines, and you can see on the board. And you can let me admit someone here, and then we will solve a couple of problems in the class in this workshop. And for those who are joined on the webinar, I'll tell you what stuff to download today in the end of today's session, in the first session around by 12 noon. And then you'll be able to download those things and be ready for tomorrow's session in case you want to do hands-on yourself while we are working on this webinar. And these sessions are recorded, and we'll share these with you on request when required. We'll also have a session on minerals processing that will be delivered by Dr. Pablo Brito Parada. He's based at Imperial College London. So he will be talking about the application areas. So I'll be telling you more about the theory and mathematics and modeling, and he'll be talking about to you about the real stuff, how this is handled in processing applications, particularly minerals processing, but some other applications as well. So you'll be able to better appreciate these problems and these applications once he discusses how industry and academia deals with these problems in minerals processing. And then tomorrow we'll have hands-on sessions where we'll cover pre-processing, so how to make a geometry, how to mesh it, and the subtleties involved with that. Then we'll talk about how to solve it using fluidity FEM solver, and what are the options available, and understand those options. And then towards the end, how to post-process it so that we can extract some useful information out of it. Right. So today, after this welcome address, we'll start with the first session at 10 o'clock, and I'll suggest you attend all of them. In case you cannot, there's no issue, but we will try to maintain continuity. So if you miss a session, it might be a little problematic for you to follow up the next session. So tomorrow we'll have 2 more sessions, as I said. In the first one, we'll talk about fluidity, the open source FEM code, how to model certain polydisperse problems using this code. And then in the second session, we'll learn how to model these systems using ANSYS Fluent, because you'll always want to benchmark your solutions, however you're solving them, with some commercial codes as well. So ANSYS Fluent is a well-accepted commercial code, so we'll understand how to model these particular kind of problems in ANSYS Fluent. I'll introduce the speakers before the talks in detail, so we won't spend time on that here. Some general notes. So we'll have plenty of time for Q&A. So let us keep it interactive, both in person here and online. Feel free to ask questions. And I'll leave plenty of time to ask. In case you would want to interrupt and ask questions during the talk, it's completely fine. Just raise your hand either here in person or online. There's an option to raise hands in Google Meet. We'll be recording these sessions because that's required as a part of the SPARC project. And if you have any questions or queries, you can always email them to me at gaurav@itmandi.ac.in. These slides, all of them, will be uploaded on the SPARC website. The webinar website. You already have seen the website where you registered for this. So we'll have a section where you can look at these slides, as well as you can look at the recordings as well in the future. Right. So that's pretty much it for the welcome address. Again, I thank SPARC, MHRD, which is Ministry of Education now, for sponsoring this project. And I also thank IIT Mandi and Imperial College for the administrative support. So any questions, I'm happy to answer that. Otherwise, after 5 minutes, we will start with the first session. Right. So today, Any questions? Yes, please. Ramajayam, you have a question?
Very good morning, sir.
Yes.
Sir, what are the prerequisites of that software to install in a system, sir? Because I
For
have to be
installing, if you have a Windows system or a Linux-based system, that should be all right. It also works on Apple-based systems if you have an Intel processor. If you have a Silicon M1 chip, that could be a problem.
okay, sir.
ARM architecture is a problem, but Intel-based machines should not be an issue. And you will require around 4 gigs of RAM. And again, hard drive, I think the virtual machine is 20 gigabyte in size. So that's the requirement.
Sir, I have one more question, sir.
Yeah.
So I'm a research scholar doing initial stage of research work in fluids only. So any other prerequisites to attend this course?
Well, if you understand fluid mechanics, if you have seen mass, momentum, and energy balance equations, or momentum equation particularly, if you have seen that, Navier-Stokes equation, that should be all right.
Okay, sir.
Some basic mathematical engineering mathematics may be required. Again, that should not be a problem.
Okay, sir. Thank you, sir.
Any other questions? Right. So we'll pause for a bit. I'll get my presentation ready for the next talk, and then we'll start at 10 o'clock. You can keep logged in if you want. Thanks. So doing an audio video check again. So for those who are online, can somebody please confirm if you can hear me, see me, and see my screen?
Yes.
Yes, sir.
Perfect. We'll start now. It's 10 o'clock. So welcome. So we'll start with the first session, that is on FE, Finite Element Modeling of Multiphase Polydisperse Flows. My name is Gaurav Bhutani. I am Assistant Professor at Multiphase Flow Research Lab at IIT Mandi in the School of Mechanical and Materials Engineering. So we will discuss about polydisperse flows first. So before we talk about polydisperse flows and talk what these flows mean, first we have to talk about what multiphase flows are. Okay, so fluid mechanics for single phase flows is something that is quite straightforward. You have water, for example, flowing in a pipe. That's a single phase flow. We can include other phases in the flows. So in the flow, for example, we can have gas bubbles which are sparged into a pipe. So you have gas bubbles inside a liquid flowing in a pipe. So that becomes two phases, so multi-phase flow. We can also have different states, gas, solids inside liquid. That becomes a multi-phase flow. We can also have different liquid phases or different gases flowing together when we have a sharp separation, sharp interface between them. So even then, in that case, we call it multi-phase flow. So oil and water flowing together also becomes multi-phase. So when we have different phases which show distinct behavior in a flow, we call it multi-phase flows. Next is what are the different phases and what are their properties. So we are looking at dispersity or something called a dispersed phase. Okay, so phases can be of two types. Let me write it down here. So for today's discussion, we'll say either it's a continuous phase or it's a dispersed phase. Okay, so dispersed phase examples could be gas bubbles. Okay, so they are dispersed inside a liquid continuous medium. It could be solid particles, again dispersed in a continuous medium, which could be either liquid or it could be even a gas. So when we talk about fluidized beds where we have solid particles and you fluidize them using a gas, so you apply some pressurized gas and then that results in the solid particles moving up against gravity and then they get fluidized. So they tend to flow like liquids or gases, fluids. So we differentiate phases as continuous and dispersed, and we are particularly looking at, so I should say phases are of two types and we are looking at dispersed phase here for this discussion. Now dispersed phase, which are discrete particles of gas, solids, or even liquid. Sometimes we can have liquid drops dispersed in a continuous gas medium or other liquid. So that also becomes dispersed. So if you can count the particles, it becomes a dispersed phase. Now dispersed phases can either have all the particles exhibiting similar properties. So let's say you have a monodispersed system. So where we have solid particles all having the same size and other properties, same material, completely homogeneous, same shapes, same sizes, so completely identical. All the solid particles are completely identical in the system. So we call it a monodispersed system. Okay. Whereas when you have, let's take particle size as the only property of interest here. So they're all spherical homogeneous particles, but of different sizes. So that becomes a polydispersed system. The polydispersity exists in particle size. So we call it polydispersed because there are multiple sizes. So we can draw a size distribution like this, for example, where here you have the size, and here you have on the y-axis, we have, let's say, percentage number. So we'll have most of the particles are of a given size. Then these particles are of these sized particles are smaller in number, and these particle size again gets smaller. As the size increases, the number of particles in your system decreases, and finally it You clip it at some point. You cannot have particles below size 0, and you cannot have particles above a certain size, which is a threshold size. So this becomes a size distribution. So this system is polydisperse, not monodisperse. Monodisperse would be all the particles having the same size. Next is, our interest today is on polydisperse systems. So next we have to understand how is polydispersity created. So it could be in the initial condition. Like you start with a system that already is polydisperse. So you start considering a system of particles, you're trying to model the dynamics of flow of, let's say, some solid particles, which already to start with are of different sizes. You have a size distribution to start with. So it's a polydisperse system based on the initial conditions. So that's one way to get polydispersity. The other is you can have boundary condition effects. So boundary condition effects are that even though you start with a system that is completely monodisperse, but some particles are entering your system, and these particles, as they enter, they bring in polydispersity. So let's say you have a boundary. So we have a cylindrical vessel, and at the bottom, we have an inlet from which gas bubbles are sparsed in, and these gas bubbles, when they enter, they are having a size distribution. So even though in the beginning we either did not have any gas bubble inside, or we had all the bubbles of the same size to start with, but as the bubbles enter, they bring in a size distribution. So that's polydispersity through boundary conditions. You are getting a size distribution because of some inlet to the in the system. So these are two ways, but they are not very interesting. The most interesting part of studying polydisperse systems is because the nature of the phenomena or whatever is happening inside the system is creating polydispersity. So let's say from the inlet you have bubbles of all 5 millimeters. Inside the system to start with, you had bubbles of 5 millimeters. Okay? So there was no polydispersity because of initial condition or boundary condition, but as the systems, as the bubbles interact with each other, they aggregate, they form bigger bubbles. As the bubbles reach some zone where you have a lot of turbulence, where a lot of eddies are there, so they tend to break into smaller bubbles. So we get a size distribution, a polydispersity, due to some dynamics that is happening inside the flow. And that is the most interesting part of polydisperse systems, aggregation and breakage resulting in polydispersity in the system, even though it was monodispersed to start with. So we'll be looking at particularly these aggregation and breakage effects, how to model them, and then learn how to simulate them in today's discussion, or in this discussion in the next 2 days. Just a quick check if everything's all right online. Good. Sandeep, can you connect to this meeting on a machine just to make sure if we are online, because I cannot see the others. So sometimes it happens that we get disconnected and I still keep on talking. Okay? So just for checking. All right. So next is motivation. What is the motivation behind studying polydisperse flows? So polydisperse flows find applications in a lot of industrial systems. I'll only talk about a few important ones, but there are many others in industry as well as sciences and nature. So bubble columns and stirred reactors. I talk about this first because we already have an image here. Plus, we'll also be discussing this application in the next 2 days for as a dummy problem. So bubble columns are used in industry for mixing liquids. It's used for reacting liquids with gases. If you want a gas to react with a liquid or gas to mix in a liquid, you'll use these bubble columns here. Some liquid, some gas will enter. Sorry, a gas will enter and then it will move up because of the buoyancy, because of the pressure difference, and then as it moves up, as it accelerates, it creates some turbulence in the system, some mixing, very interesting dynamics develops, and it is used in industry to mix as industrial mixers. Stirred reactors, again, polydisperse systems where you have a stirrer or an impeller that is used to create mixing. And as the impeller moves, it draws in some air bubbles or some vortices, and then again it becomes a multi-phase system. Fluidized beds, again, a very important industrial application. Here you have solid particles which are fluidized using gases or liquids, so that they can flow easily, or they can have more area of interaction with the gas or the liquid. So if you want some gas to react with a solid, then you will use a fluidized bed, because as you fluidize it, the solid particles, all of them, have a better tendency to interact with the gases in the flow. Sprays, aerosols, combustion, all these are key applications where you find droplets of liquids and so on, of again different sizes. And nanoparticle manufacturing. This is again, nanoparticles are extremely important, be it drug delivery, be it medicine or other applications in processing. So again, a lot of polydisperse flow applications there. Minerals processing, again, Pablo is going to talk about it later today. It's a combination of ores, that is crushing of ores. So when we extract ore, we have to crush it into smaller particles so that we can liberate the mineral out of it. So again, very important application, because when you crush any ore, you end up getting size distribution. Again, when you have to separate it or do something with it, size plays an important role. So we have to study the size distribution, or evolution of size distribution has to be predicted for these applications. Food and dairy industry, wastewater treatment, pharmaceutical industry, biochemical industry, paints, manufacturing paints, oil and gas, big industry that has a strong application in polydisperse flows, and biology. We talk about cells, which are combining with each other, cells splitting. All this can also be modeled using such polydisperse flow models. In the nature, we have a lot of applications. I'll only highlight a few of them. Cloud formation. It happens through particles interacting with each other, and these droplets growing over a certain nucleus. We have volcanic eruptions, particulate transport, long distance transport of sand or other particles of different sizes. Snow avalanches, landslides, again, many key applications of polydisperse flows, where you have particles with different properties or different sizes particularly. Right, so after this motivation, I'll quickly overview as to what we'll discuss today. So we'll start with a discussion on model equations, because we'll need to understand these equations before we start using them for simulations. Once we understand the modeling equations, we'll move on to the finite element method, the method that will be used to solve these equations. Then we will discuss some solutions. Although we'll be solving these things, these equations ourselves for certain key systems, I'll show you some solutions, because that will give us some motivation as to how the solutions look, what sort of post-processing is required. And then finally, towards the very end of today's session, around 12 noon, I'll talk about the code, how to get the code. It's a 20 gigabytes virtual machine that I've created. So for those who are here in person, you can easily download it, or it's already available in the lab here. For those who are for those who are online, we'll have to download it. So I'll include a link here. You'll have up to 1 day to download that 20 gigs of file. And then that can be used to run the software. All these software programs are installed in the virtual machine. So all you will need is VirtualBox to run the virtual machine. So we'll talk more about it. I'll demonstrate briefly as to how to do it so that you can practice yourselves today. Let's move on to part 1, that is model equations. So before I move to part 1, do we have any questions from the audience? Yes, please. Hussein Bacha, you can ask your question.
Sir, you tell the basic definition of multiphase flow. If I want to ask one question, that if there is a mold and in which there is a air and we are pumping the molten metal, then it is also a problem of multiphase flow or single phase flow, sir?
So if you have a liquid metal flowing in addition to some gas,
mold has a air,
right,
or vacuum, and we are giving inlet.
Yeah, if it has air, let's so if it has air and you have molten metal as well, so this fluid mechanical system becomes a multi-phase system, because you'll have to track that air bubbles or air particles, whatever they are, they will move, and that dynamics then becomes a multi-phase problem.
Means that
if you only have a molten metal which is homogeneous in nature, then it becomes a single phase.
There is the interaction
of
happening of air and molten metal. So this problem is considered as a multiphase flow. Means there is no mixing of air and molten metal. Means air is air.
Yes, so if even charge boundary between them, we will definitely consider this as a multi-phase system. Again, it depends. I mean, what you're trying to study. If you're only interested in the molten metal dynamics, and there is nothing interesting happening in terms of its interaction with air, then we'll consider it as a single phase system. But if both phases are interacting with each other and doing something interesting with each other, then we'll model it as a multi-phase system.
Sir, I want to analyze that the flow front is traveling, so then it is considered as a multiphase, because I want to analyze the interaction of air and molten metal here.
Let's discuss about this particular problem of yours after we have talked about the modeling equations and theory today. Is that okay?
Okay, sir.
Okay, thanks. Any other questions? Okay, so the question is, how is polydispersity relevant to snow avalanche flows? So avalanche by definition is particles of ice and rock moving together down an incline, and it is mixed with, sometimes with water, because ice melts and makes water, or sometimes it is mixed with gas. So you'll see this powder cloud of avalanche flowing. So this is this because you have two phases moving. The gas, let's say, for a powder cloud, and solid particles. So they interact with each other. So they interact with each other, and if you were to model only the flow of ice particles without considering any gas, we'll end up, because there's a lot of resistance that the solid particles will face as they accelerate, as they move faster and faster because of the gas. So this is an two-phase system. Does it make sense? So we'll have to understand the flow fields of both phases, not just one. So as a first exercise in engineering, we can model it as a single phase, but then if you want more accurate results, you'll have to model it as multi-phase. Right, so let's move on to model equations. So to understand the equations, the model equations, we'll take an example, because then it will be easier to relate the equations to the flow dynamics happening here. So we'll take an example of a bubble column. So we have this thin section of a column, which is filled with liquid to start with. It has an inlet at the bottom here. So from this inlet, gas bubbles can enter, and then as they rise up because of the buoyancy, because of the pressure, and they will tend to leave from the outlet. So the gas bubbles continuously enter and leave in this column, whereas water does not enter or leave, water stays inside. So let's assume that water is only filled till this height, so it does not splash out of the outlet. Okay, so that's our two-dimensional bubble column. It's called two-dimensional because it's very thin. So we'll consider it as a 2D system. So we only have X and Y directions. We'll neglect the flow happening in the Z direction. Okay, why that is the case, we'll not talk about it. It is just for understanding the model equations today. Realistically, the system is three-dimensional, so you'll have to include 3 dimensions, or all 3 of them. Okay, this is, so we'll be comparing our results through simulations with experimental data of Diaz. So Diaz et al. Were the people who have done experiments on this bubble column. The bubbles entering the system are monodisperse, as I mentioned in the first slide. So they are all 5 millimeter bubbles. So what will happen is, because of turbulence, we will have interaction of bubbles with each other, or bubbles interacting with the turbulent eddies, and that will result in some coalescence of bubbles or breakage of bubbles, resulting in a polydispersity in the flow. So we'll talk about those as well, and understand how those coalescence and breakage effects can be incorporated into the fluid mechanics. So here's a model summary. So we have 2 phases. We have air, that is the gas bubbles, and we have liquids. We are modeling both of them using Eulerian system. So that means they are both continuous, in the sense that if you take, let's say, a representative volume, a small volume, then it will have some amount of gas and some amount of liquid and some amount of gas, and that fraction of each adds to 1. So that's the Eulerian system. In Eulerian Lagrangian system, you model the discrete phase as Lagrangian or discrete particles. So we track each and every particle in a Lagrangian system, whereas in Eulerian system, we use this approach where we say that both are continuous phases, and they each have a volume fraction associated with them. So it's very useful modeling strategy, which allows us to incorporate particle properties as well as model the overall flow behavior. We'll talk more about it through equations. How do these two phases interact with each other? They interact through pressure. There's a common pressure that they share. They interact through a drag force. So when, let's say, a gas bubble rises up in a liquid, then it applies a force on the liquid upwards, and the liquid applies an equal and opposite force on the gas bubble downwards. So this is the drag force we're talking about here. Okay, so this is how the two phases interact with each other momentum-wise. Okay, that's another way of interaction. The third one is volume fraction. As I said, that there is a volume fraction of each inside a representative volume, and as the gas and liquid move, the volume fractions inside a representative volume will change. If the gas tends to concentrate on some part of the column, then the volume fraction there will start to increase. The volume fraction of gas will increase with time. So the volume fraction is also another scalar field through which the two phases will interact with each other, and we'll see that in the equations. So that's modeling the momentum of the two phases. Next comes turbulence. Now what happens is, in this case, we are modeling the liquid as a turbulent medium. So what that means is that if you were to measure the velocity of the liquid, what you see is that there's some fluctuation in the liquid because liquid becomes turbulent. So we measure the liquid velocity, and it comes out to be fluctuating with time. So this is time, and this is, let's say, the velocity in x direction for liquid. To handle these fluctuations and the effects of these fluctuations on the overall momentum balance, we will use a K epsilon turbulence model for the slurry. Well, actually, this should be liquid. So what this model does is it enhances the viscosity of the liquid, because turbulence by its nature is dissipative. So what it does is it increases the viscosity, and that results in an increased mixing, because viscosity, molecular viscosity, for example, results in momentum, the mixing of momentum. So similarly, since turbulence is a mixing but on a larger scale, so what we do is we add a turbulent viscosity to the liquid viscosity, the molecular viscosity, and that is the only way we turbulence affects the flow behavior in this case. It's a very standard way of modeling turbulence, K epsilon model. We will not go into much of a detail, but the idea here is we want to understand how the interaction between the models is happening. Now for solving the K and epsilon equations, whatever they are, we need the velocity field of the liquid phase or the continuous phase and the volume fraction of the liquid phase. So this is something that is required from the liquid phase models, and when K epsilon models are solved, we find a molecule, eddy or turbulent viscosity, and we feed in this viscosity to liquid field. So these are coupled models. So this is flow and turbulence. Next comes handling polydispersity. So we handle polydispersity through something called a population balance equation. Again, we look into this equation in more detail. But what this equation does is it helps us track the population of bubbles as a function of their sizes. So if I was to track the number of particles or number of bubbles as a function of their bubble size and also position in space and time. So I want to understand that at a given position in space, checking if you're connected. So I want to check if for any given position in space, what is the size distribution here at any given time. So this is a particular x, let's say xp, and at a particular time, I want to see how many bubbles are there of a given size. So we want to find a whole size distribution in a small volume, because you can have multiple bubbles in it. So some bubbles, larger bubbles may be larger in size because of whatever dynamics is happening. So we track the size distribution, as we call it. But here we're talking about interaction. So what we do is, as the population changes, as the bubble size evolves. So if, for example, we have in this bubble column, we get larger bubbles here and smaller bubbles here. the way that affects our flow model is that a drag force that we just talked about here, the drag force depends on bubble size. Larger bubbles will tend to apply a larger drag force as compared to smaller bubbles. So that information about the bubble size is there in a drag force model. So this model of population balance will feed in the bubble size to these flow models, and they will be able to better calculate the drag forces. Okay. Now, since the bubbles are moving, it could be that the gas flow field is such that all the bubbles move from left to right. Again, hypothetical, but just to understand the concept. So we require the velocity field of the dispersed phase. That is the velocity field of the gas phase. So depending on the gas phase, our bubbles will move. So there, the population balance requires this velocity field. So that is where information is fed from the flow models to the population balance model. Okay, so this is a brief initial summary of the models. I will now discuss each and every model in a little bit more detail, and then I'll come back to the summary to summarize how we put those models into perspective. Yes, please.
Here the water is stagnant in this box now, and air particle is coming. How we are saying this? How we will get this value? Particles.
No, liquid. So the question is that the liquid is not flowing in and flowing out of the column, but it is flowing inside the column. You will have some recirculation. So what happens is, as the bubbles rise up, they push the liquid, but the liquid cannot go out. So very interesting dynamics develop where you see circulation. The whole liquid starts to mix. We will not. So when you say particle, you mean gas bubbles here. Okay, so we will not talk about liquid particles because liquid is a continuous phase here. So whenever we use particles in the sense of polydisperse flows, they're always gas particles or discrete phase particles. Right. So flow equations. So we are using Euler-Euler system. So we have equations of, this is our mass balance. So since we have a common pressure field, what happens is we end up combining these equations into a common continuity equation. So we'll call it a common continuity equation. So we can assume a common pressure field, although there are two different phases, gas and liquid, but we can still assume a common pressure field, and that is allowed if the interfacial effects are small and if the interphase or the relative velocity between the phases is also small. But if the interface is, if you have a very sharp, if you have very strong interfacial effects and surface tension effects are very large, then you will see definitely that the pressure inside a gas bubble, for example, and the liquid will be very different. But if those interfacial effects are small, then we can assume that more or less the pressure is the same in both. So this is an assumption we are making here. Next is our momentum equation. Now, since we have two phases, gas and liquid, so we have two different momentum equations. So I here, the subscript I denotes the phase. So I can be equal to C, that becomes a continuous or a liquid phase, and I can be equal to D, that becomes a dispersed or a gas phase here. Okay. So again, standard looks very similar to Navier-Stokes equation. You have the transient term, we have the convection term, we have the pressure gradient term, which is coming from the stress term, and then we have the other viscous term, again coming from the stress term. And in this case, we also have an interphase interaction between the two phases, which we call the drag force. So we'll only call it FDI. It's the only drag force that we're considering in this case. Right. Okay, so this is our momentum equation. Then, since we need the volume fraction in the momentum equation, we solve it using the it's a simple advection equation for volume fraction, which comes from mass balance. And finally, we have a compatibility equation, which says that it's basically a conservation of mass again, which says that in a given volume, a given representative small volume, we have the total amount of liquid and gas fraction adds to 1. We can either have a liquid or a gas inside it, nothing else. Okay, so these are our equations of flow. Now, there's a drag force between the two phases, which is very important because this drag force, in fact, is what results in the interface dynamics. As the bubbles move in the column, they will result in the liquid making some sort of circulation inside the flow. So if the drag force was not modeled at all, then there is no interaction between the two phases in terms of interface drag. So there's no bubble pushing the liquid and liquid applying some sort of drag on the bubble. So this is a very important force, and we are using a very simple model for it. One of the oldest models called the Schiller-Neumann drag coefficient model. But latest, more useful models are available. So those can also be used. But for this discussion, we use a simple model. Okay, so in this model, we say that the drag force depends on certain quantities, which is the volume fraction of the continuous and the dispersed phase, the density of the continuous phase, the relative velocity between the two phases. Because if the two phases move together with the same velocity, that is relative velocity 0, then they won't apply any force on each other. It's only the relative velocity that results in one moving against the other, creating a drag force. And then it also depends on the size of the dispersed phase. That's where the diameter of the dispersed phase comes into the picture. And that's a very important, in some cases, that can have a significant effect. And that is the reason we need a population balance equation, to get an information of the size of those bubbles as a function of space and time. So simplistically, if one does not want to model the polydispersity in the system, but they still want to model the flow dynamics, they end up taking a monodispersed system. They assume that this particle size d is constant. But in some cases, variation in the particle size can result in a significant effect in drag force dynamics, and that whole prediction changes in terms of flow. So in some cases, it can have a significant effect. Right, so next is K-epsilon model. So I mentioned that we're talking about turbulence here, so it's statistical in nature. We have fluctuations in the flow. So we write the overall, we substitute the overall flow field as a sum of a mean and a fluctuation, and we do a time averaging, or called Reynolds averaging, and then we apply that to the whole equation of momentum. So when we do that, again, we won't do it here, but what you are doing is you are writing this velocity as a sum of these two quantities, and then you apply this averaging over the whole equation. You integrate the whole equation over a certain time, capital T, where so that capital T is much larger than the fluctuation times. So what we see is we get an equation for the average flow velocity, and we are happy as engineers. We are happy with how the average flow velocity changes with space and time in the flow. But in this process, we end up getting a new term, which more or less tells us that the interaction of the fluctuations feeds in to the average flow. Okay, so this is where the turbulence has an effect in the average flow behavior. So one has to understand how to model this, and in the K-epsilon model, we use a simple Boolean-esque model where we say that just the way laminar or molecular shear is modeled as molecular viscosity times the rate of strain, we model turbulent shear as some turbulent viscosity, whatever that is, some viscosity times the rate of strain. And that turbulent viscosity, so the problem now boils down to finding this mu t for the given phase I. That is liquid phase, because we are considering turbulence only in the liquid phase here. And how do we find this turbulent viscosity or eddy viscosity? We use turbulent kinetic energy and turbulent dissipation rates rate equations. I don't want to go into details of this equation, but what you can understand is that these equations help us find molecular viscosity. So we'll write, turbulent viscosity. Turbulent viscosity as some function of K and epsilon. Okay, and once you find K and epsilon by solving these equations, you can find turbulent viscosity, and then the system, the Navier-Stokes equation or the momentum equation that we are solving, we simply add. So overall viscosity becomes molecular plus turbulent. Okay, so while solving these equations, turbulent viscosity is different from molecular viscosity in the sense that it is a model, it is not a physical reality. The other is turbulent viscosity is non-homogeneous. So molecular viscosity, you take a liquid, its viscosity is the same everywhere. Liquid is flowing, it's the same. But turbulent viscosity is different because it's a function of turbulence, the amount of turbulence. So if the amount of turbulence is more in a given region in the flow, then turbulent viscosity will be more. And this has numerical importance because when we solve the equations, we have in some cases, as we might see today, that we have a gradient operator, and then inside that we have molecular viscosity times something. So earlier what we used to do was we used to take this out because it is not a function of space. But now since you have a turbulent viscosity here, you cannot take it out. It is not allowed because it has a gradient involved. So gradient of molecular turbulent viscosity, gradient of turbulent viscosity is non-zero because it is changing in space. So one has to keep this into mind. And again, while choosing the models and fluidity tomorrow, I'll show you where we can decide this. Good. So the last discussion, last model, and the most important discussion that is the whole aim of this webinar or workshop, population balance equation. Population balance equation, if we try to understand in a very simple term, it's a simple number balance. Like we have mass balance, we have momentum balance. This is population balance or number balance. Population of certain bubbles. And we tend to do some balance out of it. So N here denotes particle size distribution as a function of external coordinates as well as internal coordinates. So let's say this is the number of bubbles of a given xi coordinate. So xi in most cases can be particle size. So we can say that the number of bubbles of 5 millimeters is 100 and the number of bubbles of 2 millimeters is 500. So this is a way to say that we're talking about the number of bubbles as a function of its size in a given representative volume. It could be the complete volume, it could be a small volume in space. Now this xi could also denote some other properties. So let's say we're talking about particles which have shapes which are changing. So I say that particles with spherical shape or close to spherical shape have an X amount of or X in number, and particles which are non-spherical in shape are Y in number. So then in that case, xi can be shape. So xi does not need to be only particle size. It could be particle area. So when we have particles of different shapes, we tend to take xi as the particle area because quantifying shape is much more difficult than quantifying the area. Okay, so we tend to take area in that case as well. Sometimes we take two internal properties, xi1 and xi2. So in that case, we can have the shape as well as its area. It could be other property like temperature. So we can say number of particles having a given temperature are X and number of particles of a different temperature are Y, and so we have a complete distribution of those. Okay, so the idea here is xi can be anything, but in most cases we take it as a particle size. It is an internal property or a property of the particle or a dispersed phase. All right. So in today's discussion, we'll take only one xi. So we have So in today's discussion, we'll only have one internal property, only one xi, that is a particle size or the bubble size. So this representation is called a monovariate or a univariate population balance equation. But if you have more xi's, so then you get a bivariate or multivariate. So bivariate is when you have two internal properties, xi1 and xi2. And similarly, we can have multivariate where you have multiple xis. But today for this discussion, we'll only talk about single xi. Right, so let's understand the equation now that you understand what n means. So we're talking about the evolution of the population. So when I say evolution of the population, I want to understand how n is changing with time. So we're trying to understand this transient behavior del n by del t, and how is n changing with time. And that is a function of many things. That is a function of advection. So if my bubbles are moving because of flow field from left to right, for example, in that case, what happens is my population at a given point in space will change. Because if the particles, the large particles move from left to right, on the right hand side, my large particles will increase with time. Okay, so that's the advection effect or the convection effect. Then we have the growth effect. If at any given point in space, the particles are growing in size, there could be some dynamics affecting the growth. So then that is a growth term in the population balance equation. We have diffusion. Some physical phenomena could be modeled as, actually it's dispersion, not really diffusion, but it could be diffusion in both external and internal spaces. So diffusion in external space, external refers to the particle position. So diffusion in external space is more obvious. So let's say you keep a gas, and with time the gas is mixing, it's diffusing in space. So that's physical diffusion. You can also have internal diffusion, which is more difficult to understand, but that's more of a modeling concept, where your number is changing in the internal space. So in the xi coordinate. So I start with particles of a given xi, but then some of them become larger in size, some of them become smaller in size. So that's a diffusion in the internal space. So we won't discuss much about it. That depends on the physical phenomena, whether we need this diffusion model or not. But for today's discussion, we don't need that. The most interesting part of population balance equation are these right-hand side terms, also called the source terms. So this is where the breakage and coalescence effects of bubbles come into the picture. So this capital B here denotes birth, and capital D denotes death. Let's understand these terms. So the subscript here, this B denotes breakage. So this BB denotes birth due to breakage. Let's see if I have these terms in more. Okay, I have these terms in more detail in the next slide. So let's talk about them. So this is birth due to breakage. So what that means is, if I go back to my previous slide, we're talking about how the evolution of n as a function of xi, x and t is happening. So what we are saying is, what is the contribution due to breakage for particles of a given size xi? So the way particles of size xi can happen from breakage is if a bigger particle breaks into a smaller particle of size xi. Okay, so particle distribution of sizes xi1, where xi1 ranges from xi to infinity. It's only the bigger particles that can break to form smaller particle of size xi. So we're talking about the contribution of breakage to formation of particles of size xi. So that depends on the number density function of particles xi1. If there's no bigger particle, then it cannot form a smaller particle. So if n was 0 for larger particles, then there's no breakage effect. Okay, so this depends on n. It depends on some other properties as well. These are called breakage kernels. So this, for example, A denotes breakage frequency. That depends on the physical phenomena. So let's talk about bubbles. Now the breakage of bubbles depends on turbulence. Larger the turbulence in the system, the more the breakage. If you want to break bubbles, you create a mixing. You take an impeller and create lots of mixing. You get very small particles, small bubbles. So this breakage frequency has a dependence on turbulence. Okay. Next is a daughter size distribution. Now, if a bigger particle, a bubble breaks, will it form particles of equal sizes, or will it form particles of unequal sizes? What will be the sizes of particles formed if a bigger particle, a bigger bubble breaks, right? So that is contained in this function. dotted distribution function, which says what is the probability of a particle of xi happening if a particle of size xi1 breaks. All right. So this collectively, this integral will give us the birth of particles of size xi due to breakage of larger particles. Next is birth due to coalescence. So what happens is, to get a particle of size xi, particles, smaller particles have to combine, right? So we say that particles ranging from size 0 to size xi can coalesce and form particles of size xi. Of course, bigger particles coalescing will always form even larger particles. So they have no contribution. So this integral has to go from 0 to xi. And now since two particles are coalescing, we have number density of particle size xi1 and another xi prime, so that xi prime and xi1 are linked. Xi prime and xi1, they add to give us xi. They not strictly add because it's the volume we're talking about. So when two particles combine, two bubbles, spherical bubbles combine to form a bigger bubble, we cannot simply add the radii of the two particles. We say volume of first plus volume of second gives a volume of third. Okay. So it depends on the number density of combining particles, particle sizes. It also depends on a coalescence frequency. So again, that depends on the physics. So if you have a lot of turbulence, that can actually help in coalescence sometimes. So turbulence creates interaction between the phases, and these interactions then result in coalescence. Okay, so this kernel, this is called a coalescence kernel, and that is dependent on the physics. So that we have to bring in from our understanding of the physics of the system. All right. So this is birth of particles of size xi because of coalescence. And next is death of particles of size xi due to coalescence. And how does that happen? When a particle of size xi combines with any other particle of size xi1, let's say, it dies. That's outflux. Since we are gaining particles of size xi, we are also losing, because currently whatever is of particle size xi is combining with other particles and leaving the particles. So that xi1 ranges from 0 to infinity, because our current particle of size xi can combine with any size particles, and that results in the death of that particle. So that numbering decreases. And that again, since it's coalescence, we have a coalescence kernel. And we missed one. We missed this. That's the death of particle of size xi due to breakage. And that is very simple. A particle of size xi breaks because of some breakage frequency, and it is gone. So collectively, these four effects, these two effects of coalescence and breakage, they bring in four source terms into the population balance equation: the burst due to breakage, birth due to coalescence, death due to breakage, and death due to coalescence. So for solving the population balance equation, we need breakage kernels as well as coalescence kernels. And as I said, for a current problem, they depend on turbulence a lot. So they will be dependent on physics of the phenomenon. So they have to be modeled. They cannot be obtained from some fundamental. Well, they can be obtained, but for the current kind of population balance, the system that we have to bring in those models from somewhere else. So an experimentalist might be doing some experiments on the interaction of two particles under some controlled turbulence. So through those controlled experiments of two particles under controlled conditions of turbulence, or somebody might be doing a DNA study, a direct numerical simulation study, where they resolve all the times and spatial scales and understand the interaction of two bubbles in a controlled turbulence system. So they will tell us, they will give us these kernels of breakage and coalescence. And then we can, because we want to model an overall flow, right? So we cannot resolve the motion of each and every particle at each and every scale. So that becomes computationally very expensive. That is the reason we are bringing the population balance equation into the picture, because this mesoscale equation helps us solve the macro scale Eulerian equations. So the underlying idea is that coalescence and breakage kernels have to be brought from some physical understanding of the phenomenon. You can go to previous research papers where people propose new models, and then you can use them in your system and try to understand or develop a model and validate it against experiments. So this was the discussion on the physics of these equations. Do we have any questions? Now we'll move to the mathematical nature of this equation. The drag force? Yes. Yes.
We are taking Reynolds number.
Let me go back to that slide. Yes. Yes.
Reynolds number late.
Yes.
Sir, this is applicable for gas as well as solid or gas or yes.
Well, this was actually developed for solids. This was developed for solid spheres moving in a liquid continuum. That's the reason I said it's the simplest model available, developed in 1940s. But what we do is we tend to apply it. It's such a simple model that we tend to apply it for gas liquid flows as well. But there are better models available, so you can go to those models. So this model simply says if Reynolds number is less than 1000, this is how your drag coefficient behaves. If it's above 1000, then it's simply a constant. Right. Let's clean it a bit. I just want to clean one particular term and then discuss some mathematical nature of this equation. So let's look at burst due to breakage. And let's try to substitute that mentally into the population balance equation we have here. So if I substitute this burst due to breakage here, what we see is it becomes an integral differential equation, because I have derivatives with respect to x, time, and as well as xi as well. So actually I didn't tell you, but these terms, they bring in derivative with respect to xi. So what we have is we have derivative with respect to time. We have this gradient is spatial gradient operator. So we have derivative with respect to space, x, y, and z. We have derivative with respect to xi. And we also have integral with respect to xi that we see here. Life's actually becoming very complicated mathematically. It's an integral differential equation where the number of independent variables is larger than what we have in our simple Navier-Stokes equation. I'm saying simple Navier-Stokes equation because Navier-Stokes mathematically looks much simpler now, right? Or any other transport equation, because the independent coordinates used to be x, y, z, and t, position and time. But now we have independent or the internal variable xi also as the independent coordinate. And now we have integral of that, not just differential. So this is an integral differential equation with 4 or more independent variables. It's a multivariate system. You have multiple xi values, so it's a multivariate system. So it's 4 or more. But for today's discussion, it has 3 spatial, 1 time, and 1. So it becomes 5 or more. So mathematically, it is quite complex. So now we talk about how to solve this equation, the mathematical ideas behind this. And once we discuss this, then we'll go to FEM after a short break. So the most natural way to solve population balance equations is to use a classes method. So we have particles of many sizes. So we have a complete size distribution actually, like this. So what we say is, let's have some discrete number of classes. So on this size axis, I say, let me break it into some representative classes. So what I'll do is, I will represent each class with a corresponding number of particles. A number, of course, is an integral over an area. I'm just simply presenting values here, but this is your small n. So classes method, what it does is it uses some 20 to 30 classes of particle sizes, and then that population balance equation becomes 20 or 30 equations, because now you are tracking the number of particles of each class. So number of particles of class, not xi, but let's say number of particles of class 1, number of particles of class 2, number of particles of class 3, and so on. So you see, you have 30 transport equations, each denoting the transport of the number of particles of a given class. It's computationally very demanding, because now their classes are talking to each other, they're coupled. Because a smaller particle is combining with another particle to make another particle. So it could happen that N1 and N2 are combining to give N3. So what we see is that they are coupled advection diffusion equations, 30 of them. Computationally, that becomes quite demanding. But the good thing about that is, since you have, let me show you using a different color here. So let's say the red one, in this case distribution, was the initial distribution. Now after some time, at a given point in space, you see that these number of particles increased, these remained the same, this decreased, this increased. This is what we had. So now the distribution looks something like this. The distribution has changed. The distribution is evolving with time. That is what we are solving. You're solving for n as a function of space and time. So it is easy to recreate n. If you want to recreate the complete number density function, it's very easy. You solve for individual classes and then you combine them to form one complete number density function. But we don't always need, because see, what was the aim of solving population balance equation in the given problem? It was simply to get a particle size as a function of space and time. We want to use it in the drag model, right? That's the only use. We don't really want to see how the particle or the bubble size is evolving with time. We may need that, but in this case, we don't really need it. All we need is a good estimate of the bubble size at different points in space. Okay, so all we need is to understand the bubble size. So this classes method, although very simple in terms of its representation, it is very demanding computationally. So we go to another method, which is what is used. That's called the method of moments. Here what we do is, rather than tracking discrete classes or the complete n, tracking complete n is very difficult because it has xi in it. We use moments and track these discrete moments of the distribution function. So well, this is our statistics 101, but the kth moment of any distribution function n, for now you assume that n is only a function of xi for this calculating moments. So n being a function of xi, the moment kth moment is calculated this way. Now why do we track moments? Because moments have some physical significance. So m0 denotes the number of particles. If you think about it, if you simply integrate n xi d xi, xi going from 0 to infinity, that is for all the particles, all you get is number of particles of all the sizes. Okay? And then m3 denotes the volume of, overall volume of particles. m2 denotes an overall area, surface area of particles. So they have some useful physical significance, these moments. And in fact, we can take ratio of these moments, for example, m3 by m2, that gives us something known as the Sauter mean diameter. That's a representative diameter of particles which are non-spherical in size. How will you find representative size or diameter of non-spherical particles? You take the overall volume, you divide that by the overall area. That gives you an overall estimate of size in a given representative volume. So this is happening over a small volume. So for different volumes in space, you have different size estimates of particles or bubbles. By the way, when I say particles, I mean bubbles. They are the same for this discussion. Okay, so moments have a physical significance, and moments with this ratio m3 by m2 gives us Sauter mean diameter, and that is exactly what we need in our Eulerian drag force model. So we go for the method of moments. So the method of moments with as few as 4 moments is enough to give us something which is accurate enough to proceed. Whereas for method of classes, we have to go for typically 20 to 30 classes. If you have a very strongly changing distribution, you have to go for even more number of classes. So method of moments is the chosen method in the industry as well as academia. A lot of research happens on this method of moments. So what do we do in method of moments? Rather than, let's go back to the population balance equation. So in this population balance equation, we are tracking n. So what we do here is, we say we'll integrate this complete thing So basically we take the kth moment of the equation and you simplify it. So what that will result in is a transport of kth moment, and then that depends on some things. So rather than solving for the transport of n, which was a function of xi, we solve for the transport of the kth moment, which is not a function of xi. So we have eliminated the xi from this equation by integrating over xi. But then since you are solving for a couple of moments, so we'll have this for, let's say, m1, then we also have one for m2 till m3, m4, and you can even go higher if you want more accuracy. So we have multiple moment transport equations coming out of this single population balance equation. So that's called the standard method of moments. But what happens is, let's stay on this slide. I need to write something. What happens is when you solve for these transport of, let's say, a kth moment, this del m by del t on the right hand side has terms which not just depend on the kth moment, but they also depend on, let's say, k plus 1th moment, k plus 2 moment, and so on. So what happens is, let's say you're solving for, you're only considering 4 moments, m1, m2, m3, and m4, or m0, m1, m2, and m3. And you're solving for m3. Now that depends on m4. That depends on m5. But we're not solving for m4 and m5. So this results in a mathematically open system. We have to close this system. Otherwise, our moments depend on higher moments, and that ways we have to solve for all the moments, infinite number of moments. That becomes equal to solving for the complete population balance equation or the complete method of classes with all the sizes. So the closure problem here is to estimate or to approximate higher moments in terms of lower moments. If I can represent m4 as a function of m0, m1, m2, and m3, if I can represent m5 as a function of m0, m1, m2, and m3, and so on, I have closed the system mathematically. Okay. So now is when we need mathematical closure to this moment transport equation. So there are many methods that have developed: quadrature method of moments, direct quadrature method of moments, conditional quadrature method of moments, and many other. Sectional quadrature method of moments. So we will be discussing one particular method called the direct quadrature method of moments. So what it does is it approximates your n. So this is an approximate. Your n as a sum of delta functions. Let me draw it and represent to you. So n is a distribution, right? We approximate this as we say that rather than having all the sizes, we'll take one of these. So this we call xi1, and this we call xi2. Use a different color. Now this is a very bad representation because direct delta function goes to infinity. And what you're doing is you are saying that some amount of some weight of, so I'm representing this weight as a height here, but of course it's a wrong way to represent because it's a direct delta function. But what we say is some amount of xi1 and some amount of xi2 will give us, it's an approximation to an overall continuous number density function. You can think of it in terms of quadrature. You have a continuous function, you want to integrate that, you take the method of quadrature where you say that rather than integrating over the complete x coordinate, you take a couple of discrete abscissas and you say some amount of, some weight of xi1 and some amount of xi2, some amount of xi3 and so on. So I am representing this in terms of, for example, our n is 2 for this figure. It's a very natural way to represent. Now, what effect does it has? Well, let's see. Let's see what happens if we calculate. Do it here. I calculate kth moment. So kth moment is integral xi to the k n. So in this case, it simply becomes summation alpha goes from 1 to n w alpha xi alpha to the power of k. That's the property of direct delta function. When you integrate direct delta function, that gives you, it takes the value of wherever the direct delta function is non-zero. Okay. So basically what we are doing is we are approximating integrals as quadratures. And now as time evolves, as you move in time or you move in space, what we say, what we basically do is, let's use another different color. So after some time, it may happen at that particular point in space that the amount of, well, the xi1 may change and xi2 may change. So we have a different amount of xi1 and different amount of xi2. So rather than tracking n, in this case, we are tracking the weights and the abscissas. Well, this is weighted abscissa. So this sigma alpha is w alpha times xi alpha. Okay. So the overall mathematical problem now becomes, so rather than tracking n or actually one of its moments, we're tracking weights and abscissas. And if you have this weight and abscissa, you can find any moment out of it, right? Because moment is a function of weights and abscissas. All right. Any questions on that?
Here we are by taking, well, what we are
So the question is, in method of moments, we eliminate xi. What were we eliminating in method of classes? Same xi. Because when you represent the number balance for a given class, xi is gone. Because now you're saying that this is for xi equal to some value. So xi is gone, right? Any other question? Right. Okay, so let's clean this a bit. So what we do is, now that we have given an approximation for the number density function, we substitute this into the population balance equation. Going back, so this was our population balance equation, where the right hand side terms are all integrals. Birth and death functions are integrals as represented like this. So when you substitute this n, it's a very rigorous mathematical exercise. But when you do that, the problem becomes simply transporting our weights and abscissas in space and time. And once you understand how the weights and abscissas change in space and time, you know how n changes in space and time. Right? So our finite element solver, all it will do is it will solve these transport equations. Now, if I take capital N equal to 2, then I have two weight fields or weight functions, and I have two abscissas. Abscissa fields because it's changing with space and time. So I need two weight equations and two abscissa equations. So I'm solving 4 equations similar to 4 moments. And the right hand side of these are related through a linear system. So these A alphas and B alphas are solution to this A alpha equal to D system, where A is a matrix and D is a vector, known quantities. So all the effect of breakage and coalescence, they are in this D vector. And this A vector, A matrix, this contains information about abscissas only, abscissa values. So using the previous time abscissa values, you can get the abscissa and weights at the next time. For a given time, you solve this, you get your A alphas and B alphas. You substitute that in this equation and you get the weights and abscissas for the next time. And this process continues. Okay, so that's the way we solve for weights and abscissas, and hence the any other moment. Remember, what do we want to find? We want to find the shorter mean diameter, which is M3 by M2. And M3 and M2 can easily now be represented using this weights and abscissas. So this completes our discussion in the first part of session 1, that was on the model equations. So let's take a couple of minutes of break. Let's take 5 minutes of break, and then we'll convene again and discuss the second part, which is going to be on finite element method for solving these problems. If there are questions, I'm happy to answer them. Yes, Hussein Badsha, question.
Sir, why we are using finite element method, not finite volume method for this?
Let's talk about it when we move to that. So when I talk about FEM, I will discuss why we use this particular method.
Okay.
That will be the first topic in discussion after 5 minutes. So any question related to the population balance equation or the method we use to solve it before we move to discretizations?
Here the air particles are breaking and heading. But what will happen there? Still the particle size. So same question.
It's a very good question. I mean, you're saying you're taking a particular application of debris flows, but let's take a general application. So the question is, if we are not interested in how the particles are breaking and aggregating, then do we really need population balance equation? Right? Is that the question you want to answer? Ask? Yes. Now, see, even in this problem of bubble columns, we are not really interested in many cases, not interested in how the bubble size is evolving. But that size has an effect on the flow dynamics. Because when the gas bubbles and continuous liquid field, they are interacting with each other, the drag force is dependent on the particle size, bubble size. Now, in your application, it could be the case that even though the particle size distribution is not of much interest, but that distribution has an effect on something else that is of your interest. So you have to ask yourself that modeling has to happen first. That what do I need to find? If you simply want to find the overall amount of flow that happens, you don't really need to solve this. But if you need to solve the flow fields, then it may be of interest. But then again, you have to see whether these rock particles, when they fall down a distance of, let's say, 5 meters, not very high, that 5 meter fall may not be a strong function of the interaction with air. But if it's falling over 100 meters, then after some time it may reach a terminal velocity. So then that drag of the rock particle with air has a significant effect, right? The same rock particle, when it falls to atmosphere, has a very strong effect because of interaction with the atmosphere. It starts glowing, it becomes very hot because of friction. But if it falls over 1 meter, so that's modeling. That's where the modeling experience comes.
In case of W flow flowing from my so the interaction between the mountain and the W flow will be important for the drag force between air and
I don't know. Well, that is your field. You have to figure out yourself. I cannot answer that question for you. I may answer it incorrectly, so I will not answer it at all. So the question is, if a rock particle or a collection of rock avalanche happens over a surface of a mountain, is it important to consider the interaction of rock particles with gas or with air? I don't know. That depends on if it is important, and that effect has a strong relation with the particle size, then you need this equation. And again, that depends on how long a distance it has to travel, not just a function of. So time scales have also matter. In a small distance, maybe not. For a larger distance, my feeling is yes, because after some time you see that these smaller particles, they tend to have some sort of saltation. I mean, they will just mix with the air, so that effect is generated. Yes, Ramajayam, you have a question?
Yes, sir.
Yes, please.
So the moment we are talking about m plus 1 and m, I think. What about the m I minus 1, sir?
I'm sorry, can you say that again? I couldn't hear you properly.
So the moment we are considering about the Phoebe is about m at I plus 1, why not I minus 1?
I plus 1. So I here denote these on this slide. Again,
No,
I'm sorry, I could understand the question very well. Can you say it a little differently?
Yeah, actually, we are considering the moment to solve the problem is at k moment and k plus 1, right?
Okay, so we are considering a certain number of moments. Yes.
From 0 to infinity.
Not infinity. I mean, if we take all the infinite moments, then there is no point in using this method. We want to use a finite number of moments,
Okay.
and then represent the whole system, approximating it using finite number of moments.
Okay. What about the previous moment?
So let's say the example that I will take today, when I show you the results, we have taken 4 moments, M0, M1, M2, and M3.
Yes, sir.
Just 4 of them.
Yes.
So if you were to use a quadrature method of moments,
Okay.
where we track the evolution or track the moments, transport the moments in space and time, then the closure problem happens. So we use a method where we write our integrals in terms of weights and abscissas. So if we have an integral, so what is, let's say we get M5. M5 is xi to the power of 5 times n times d xi. So what we say is that we'll write it in terms of weights and abscissas. So this becomes over a finite number of weights. So let's say W alpha times xi alpha. So I need 4 values,
Yes,
W1, W2, xi1, and xi2 to represent the 5th moment. Sorry, this is to the power 5. And I can find W0, W1, W2, xi1, and xi2 from my first 4 moments, M0, M1, M2, and M3. And since I'm solving for those moments, I can find my W's and xi's.
Yes, sir.
Does that make sense?
Yes, sir. So we need initial condition alone. We can find out the another moments.
we need initial condition. So M0, M1, M2, and M3, we need initial condition as well as boundary condition for these moments because we are solving equations for these moments. Now we're talking about quadrature method of moments. This direct quadrature method of moment is slightly different because we don't solve for M0, M1, M2, and M3. We solve for directly the weights and abscissas. Because ultimately you need these weights and abscissas in your calculation of any moment, not just first 4 or higher. Any moment can be calculated using W1, W2, Xi1, and Xi2.
What
So
about
we transport these weights and abscissas directly.
what about the weightage of the error, sir? Will it produce more?
What about
The weightage of the error. This method.
the error?
Yes, sir.
Yeah. So the error, what happens is as you increase the number of alpha value, that is the number of weights and number of abscissas, the error of course reduces.
Okay.
Because it's a simple, it's a quadrature problem. So if you represent an integral using larger number of quadrature points, then your integral approximation is much better.
Okay. Yes, sir. I understood. Thank you, sir. Thank you very much.
Thank you. Right. Yeah. Any other question? Yeah, Hussein Bacha. Question?
Sir, I want to ask that you have defined the physics and mathematical model. Here, what are the inputs and output we are getting interesting now? Means
Input in the
means if
population balance. Right. So in this population balance equation, now this is a good question. If we think in terms of a modeling strategy, what is the input and what is the output? So the input is everything except your number density. So of course, you will input the number density as a function of, you will need initial condition. So you need in your whole domain, what was the number density to start with? And then you need, when in the boundary conditions, when gas bubbles are entering, are they entering as a monodisperse system or is there a distribution for the inlet as well? You need that. So these are initial and boundary conditions. To solve any differential equation, you need these. The other things you need is the breakage and coalescence kernels in the representation of integrals. Because these things such as A, B, beta, so these are dependent on the physics. As I said that if you're talking about aggregation of coalescence of bubbles, there's a different model. If you are dealing with aggregation of, let's say, powder particles, some sintering of powder particles, the physics is very different. So these terms are very different. So they're coming from physical models. So these also have to be supplied as physical models to the overall population balance equation model. Does that answer your question?
sir, what are the outputs we are going to interested in?
Output is our number density function. Well, the way we solve it, we solve to get T32. So this is our output. This is the only output we get from the population balance equation.
Okay, sir. Thank you.
These are important questions because while discussing equations, we sometimes forget what was the model input and output. So thank you for asking this question. So now that we've talked about the population balance equation, this slide I will discuss tomorrow when we actually solve the same problem that is shown in the slide. But what I want to discuss here is that to understand a correct implementation and sometimes to appreciate the solution methods of a given population or given equation, we try to solve an equation or a special case of the equation where analytical solution is available. Now that might be very rare, but if you can find one, that is a big contribution that you have done to find a special case of the equation where analytical solution is available. Then for that particular special case, we solve using our code and we also compare with a benchmark that is in our case ANSYS Fluent. So here you can see that the analytical solution using our code and solution using Fluent, they're all overlapping. So this was done long ago when we implemented this method 8 years ago. Now it's accepted, it's been well tested, but it's a general idea that we'll be solving these simple problems to compare the solution with analytical results. And once we have confidence in the correct implementation, then we go on to solving new problems where the analytical solution does not exist. And that is the reason we are implementing all these things to solve problems where we cannot solve them analytically. Okay. So this was our model. So we talked about the flow models, the Eulerian flow equations. We talked about the population balance equation. We talked about the K epsilon equation. And I said to you that the kernels, the breakage, the coalescence frequency beta, the breakage frequency A, they depend on the amount of turbulence. So they will be functions of K and epsilon. That is where the coupling between the turbulence model and the population balance model takes place for this particular gas column. Right, so now let's move on, change gears and move on to a mathematical discussion on finite element methods for solving fluid flow problems. So for discussion purposes, we can represent any fluid mechanics transport problem using a transport problem that looks like this. Now this is a scalar transport. This is a transport problem for scalar psi. So we have a transient term, we have an advection term, we have a diffusion term, and we have a source term. So using this representative mathematical advection diffusion source equation, we can represent transport of mass, we can represent transport of momentum, well, the transport of x momentum, y momentum, and z momentum, x momenta, y momentum, z momentum, because we have a scalar here. We can also represent transport of temperature or the energy equation. And we can also represent the transport of our weights and abscissors. So this is the most important equation mathematically when talking about fluid mechanics in general. So any fluid mechanics book will start with this kind of an equation, and then there are subtle differences. I mean, things may change slightly, but overall the mathematical nature will be very similar to any transport equation that you have. If you can understand the behavior of solving this equation, then you can understand behavior of any equation. Okay. Now to understand the approach, we'll simplify it further. What we say is, rather than having a three-dimensional nature, we'll only have a one-dimensional nature. And we will, for this discussion, we will say that it's a steady state system. We'll assume that there is no convection. So all we are left with is a diffusion term and a source term. And that is what this equation has. It's a diffusion term and a source term. This is again purely to understand the finite element approach. For a general case, you'll have to add more terms to it. But if you understand the approach, because understanding finite elements for fluid mechanics is slightly different from the way we understand that for solid mechanics. So I am using this Poisson equation for explaining how finite element approach works in fluid mechanics. Now we'll simplify it even further. This Poisson equation for now was for a three-dimensional system, but we'll simplify it to one dimension. So we have del 2 psi by del x2. So what happens is, instead of a three-dimensional domain, you have a line over which your psi values are changing, and your domain is simply between 0 and 1. 0 and 1, boundary is not included. So x varies between 0 and 1, and over this x, our the function psi changes. It could be anything. So we want to solve for this equation. And if you go from 1D to 3D, you get this equation. And if you go from this Poisson equation to a general transport equation, you get this equation. So let's discuss the finite element method for this one-dimensional Poisson equation. So this equation that we have, this equation is called the strong form of the equation. So this is a strong form. That's the equation in particular. But in finite element, we do not solve this strong form. We solve a weak form. And this equation is called the weak form. So what we do is, we integrate rather than solving for this equal to 0, we integrate this over the whole domain and multiply that by some known test functions. This is called a test function. And we equate that equal to 0. So rather than solving the strong form, we solve the weak form. Now, in this very short discussion, I cannot establish the fact that the solution of weak form is exactly identical to the solution of strong form. That requires some mathematical discussion, but you can take my word for now that the solution to the weak form will give us the exact solution to the strong form. Why we do this, that I can tell, and that I will discuss in the slides to come, that why are we solving for weak form and not the strong form. But they both give the same solution. And remember also the fact that we are solving for psi. So this is unknown. And this phi function that is chosen by us, this is a known test function. We call it test because it's a we can test different functions here. So phi is known, whereas psi is the unknown. Right. So accepting the fact that weak form gives us the right solution, we now integrate the weak form by parts. And when we do that, this is what we get after integration by applying integration by parts. Now, the reason we do this is we want to get rid of the second derivative of psi. So what we have done is, very smartly, we have reduced the equation, which only now has del by del x of psi, as opposed to del 2 by del x2 of psi. So that was a major motivation here. We wanted to reduce the derivatives from second order to first order. Not the only motivation, but the major motivation. Good. So when we do that, in the process of integration by parts, we get this term where we need to know the boundary conditions, because finding the value of del psi by del x at boundaries 0 and 1 is boundary condition. It's basically knowing the derivative of psi at boundaries, or it's called the Neumann boundary, knowing the derivative. So what we do is, now the actual boundary may not be Neumann. So when I say Neumann, I mean the derivative of the unknown is known, and Dirichlet means the value of the unknown is known. So for this discussion today, we say that x equal to 0, which is the first boundary, is Dirichlet. So we know the value of function psi at the x equal to 0 boundary, and x equal to 1 boundary is Neumann. So that means we know del psi by del x at the x equal to 1 boundary. We are solving for psi in between 0 and 1. At 0 and at 1, they are boundaries. We need to know the solution or its derivative. Now, since the test function phi was our choice, so we choose it wisely. We say that we will choose phi in such a way so that it vanishes at x equal to 0. So what that means is, we choose the test function in such a way so that it is equal to 0 at Dirichlet boundary. Okay, so this in this term, at 0 boundary, since phi is 0, so this becomes 0 at 0th boundary. For the first boundary, that is this one, we know del psi by del x. That's what Neumann means. So when you simplify it, all we are left with is this term, where B1 represents del psi by del x at x equal to 1. Okay, so this all came from applying integration by parts of the weak form. Another interesting thing that we see here is that boundary condition naturally enters the equation. If you have by any chance used a finite volume or finite difference method, what you see is boundary conditions have to be applied separately in the overall discussion. Here the boundary conditions, at least the Neumann boundary condition, entered the equation by itself very naturally. So in finite element method, we call the Neumann boundary condition also as a natural boundary condition. They automatically enter the weak form. You don't have to apply it separately anymore. So let's move on. So we have established the weak form that we will solve. Now a couple of points to note. The first one is this weak form holds for all phi. It should hold for all phi. Phi was our choice. But it is not the case that it should hold only for certain phi. When I say for all phi, I mean all phi in a chosen function space. So if I choose a function space, let's say the function, the space of all linear functions, or the space of all quadratic functions, whatever I choose. If I choose, then it should be true for all functions in that space. Okay, because phi was arbitrary. And the good thing here is, if you look at the weak form here, or let's look at the weak form when we started this one. If the integral of a function phi times something is 0, and that phi can be anything, then the only way this is possible if that thing in the parenthesis bracket is 0. It's a slightly heavier concept to grab in a very short time, but what we're trying to say is, you forgot about the integral also. You say that if some known quantity times something else is equal to 0, and this is true for all known quantities, then the only way this is possible is when that second quantity is 0. So what that means is when this is 0. So it's some way telling us that the weak form gives us a solution to the actual equation. Not strictly, mathematically it needs more work, but intuitively, if it is true for all test functions in a given chosen function space, then that means that the solution of this equation gives us an actual solution to the strong form. Neumann boundaries are handled naturally, that we just discussed. Now the exact solution of psi also lies in some function space of our choice. That choice could be, let's say, linear functions, linear polynomials. Okay. So we say that we'll try to write our psi as a collection of linear polynomials. But see, psi, the exact solution is continuous in nature. That means for all x values, you have a psi. Since we're talking, we want to use computers, we cannot work in an infinite dimensional space. So what we do is we go from a function space which has infinite dimensions, which is continuous, to a finite dimensional subspace of that. So what we say is that rather than predicting a solution which is continuous in nature, we will try to predict it. Let's say if this was the actual solution, I will want to approximate it as a collection of five lines. Okay, so I say that I have these regions 1, 2, 3, 4, and in each region I will use a first order polynomial or a linear polynomial to approximate the solution, and I will collectively find the overall solution as a collection of these linear polynomials. Okay, so now you have how many polynomials? You have 1, 2, 3, and 4. So it's a finite dimension. If it was a continuous function, the red one that you actually wanted, you need infinite number of lines to approximate a smooth curve. So that becomes infinite dimension. Okay, so we come to a finite dimensional subspace, which we denote by psi with a tilde on top. This was phi. So that's another idea that we'll be working with computers. So we tend to use finite dimensions rather than infinite dimensions. So we get collection of linear polynomials. It could be quadratic as well, but again finite dimensional. Now phi, the test function, was our choice coming from a function space. Psi, again our choice. If we choose them from coming from the same space, it becomes more convenient, and that is called Galerkin finite element method. So the word Galerkin is there because our test functions and trial functions, which are functions used to represent psi, so these are called trial functions, they are coming from the same space. Now coming to the most important idea. Now you see that I've been talking about linear polynomials. I want to use linear polynomials to represent my equation. Now if I was using the strong form and I use linear polynomials, I get nothing. You take second derivative of a linear polynomial, you get 0. So we cannot use linear polynomials to represent smooth functions if you are using the strong form of the equation. But in a weak form, you only have first derivative of both phi and psi. And they're both phi and psi and Galerkin FEM are coming from the same space, in our case, linear space. So derivative of linear is constant. Becomes very easy. Life becomes very beautiful because these derivatives become constants. Mathematically, you can get an idea that if you take derivative of a linear polynomial, you get a constant. You have to deal with constants. It becomes very easy. Okay, so that was one of the major motivations in using a weak form rather than strong form. But if you are using, let's say, quadratic polynomials, then that benefit is not there. Yes, that is what I just said. So if you are using quadratic polynomial, then you can use. But since we want to keep life simple, we mostly will end up using linear polynomials. Right, so now that I've given you a motivation, now we'll move slightly quicker. So since I just showed you that the representation of the finite dimensional functions psi is coming from some space. So what we do is we say that let's say our domain 0 to 1, we break it into elements. And we say that whatever the dimension of our space is, could be linear, could be quadratic, could be cubic, whatever it is. For now, let's say it's linear. So we say that we will use linear polynomials. So what we do is we take this first part and we draw a linear polynomial like this. In fact, two of these like this. Okay, one going up, one going down. And then in the second one, we again take one going up, one going down. Then again, one going up, one going down, one up, one down, one up, one down, and so on. Okay. And the reason we do these, if you look at this, one is going up, one is going down. And if I want to represent an arbitrary line like this, then I can take some amount of n1, which was the one going up, and some amount of n2. Only n1 could not give me this because n1 was 0 at one point. So I take n1 and n2 and I take some amount of n1, some amount of n2 and I give. And to get a general function, we say we have lots of n's, which are called basis functions. So we have lots of basis functions or shape functions, and we have some amount of contribution of each. Now this amount of contribution of each basis function is a variable. So now we can get any function as a collection of so let's say we have our elements like this. So now that we have chosen n's, the basis function, we can draw these lines, which is a linear representation, as by simply changing these psi hats. I change psi hat, I can fit any function. So the problem is slowly boiling down to finding the weights of some chosen shape functions. Okay, that's a very important idea in finite element method, that we choose a set of basis functions coming from a space. Linear space for us is very comfortable, and we say that we can fit any function using linear function by simply changing psi hats. So our problem simply now boils down to finding psi hats, and that will give me any function, which of course I have to substitute this into the main equation and then find psi hats based on the given equation. So this is a representation of these functions that I already showed you. So we have, these are called hat functions. So here what we are doing is basically I am showing you these functions for two different elements. So in a given element here, your function looks like this. But for the previous case, it had a contribution from a function going down as well. So it's simply how to number them. So we number them as, we take two elements together and call it one function. So these are called hat functions as well. Very standard finite element functions. And as we said that since it's a Galerkin FEM, so our test functions and trial functions, they both come from the same space. So same shape functions to represent these. Now what we do is we substitute this into our Poisson equation. So when you substitute that, since you had here we had del phi by del x and del psi by del x. Now phi hats and psi hats are simply coefficients. It's the basis function which change with time. So we get del n's by del x. We simplify this further. We take the phi's out. Now remember I said it should be true for all all test functions, all phi's. So that means that this whole thing has to hold true always. So what happens is this whole problem mathematically boils down to a linear system. D times psi equal to R. R is a known vector. D is a known matrix with known coefficients, and psi is a vector of unknowns. And as we saw that if we change our size, the weights of basis functions, we can change the function. Now remember these, we chose linear functions, right? And we have del n by del x for different n values. So if you look at one particular element, then what happens is out of the many n's, it's only two of these that contribute to a given element. One is the contribution from one going up, and the one is contribution from one going down. So what we have seen is, and all the elements have a very similar behavior in terms of basis functions, one going up and one going down. So locally, all the elements, they behave very similarly. It's only the coefficient that changes, right? It's only these psi's that change. If I go even further back, so it is only these coefficients, sorry, not this one. It is only these coefficients that are changing. These things are the same for all the elements. Agreed? So our choice of basis function was very smart. Locally, if you look at any element, the basis functions are very similar. So we need to only calculate del n by del x once for each element, and we're done. And what happens is, for a given n value, mostly it is 0. Because if you take del n by del x, and then you take it over the complete domain, it is only for one or two elements, in fact, it is non-zero. Everywhere else it is 0. And that results in a very sparse matrix here. Okay. So that's another beautiful property of these shape functions we have chosen, the hat functions, that they are sparse. They have a local nature. They only, if you take one of these n's, it will mostly be 0. It will only have hat like this. So if you take a derivative of this n, it will only be non-zero in a very small space. Mostly it will be 0. So your matrix becomes sparse. And that the reason we choose this is sparse matrices are easy to invert. We don't have to use direct methods. We can use computational methods where it is very easy to invert these. Okay. Right. So we are getting out of time now. Okay, so this is our general advection diffusion equation. We apply the similar method to get a weak form. We use FEM, trial and test function, and finally we get this matrix equation that is what we have to solve, where this C is the same as the size. These are vector of unknowns. So all we have to find is vector C using this matrix equation. So in fluidity that we'll be using to solve these equations, we can have different kinds of shape function, not just linear. So we can have P1, which is linear. We can also have P2, second degree polynomials, which is quadratic as shown here. We can have continuous Galerkin, that is, you can see they are continuous across elements. We can have discontinuous Galerkin, where at a given point, depending on which element you are, you can have different values. This is very useful to handle discontinuities. The discontinuous Galerkin can be very useful for handling discontinuous variables. Like if you have a front of temperature moving, no diffusion, only advection, purely advective equations, which are hyperbolic in nature, they are very effectively handled using discontinuous Galerkin methods. In fluidity, we can also use control volume, which brings in the benefits of finite volume methods. So we can use conservative quantities can be discretized using control volume strategy. And for discontinuous Galerkin, the good thing is since each element has its own contribution to a given node, we can do matrix inversion locally rather than doing globally. So mathematically that becomes easy. But it has more number of points, so we have more degrees of freedom. So we have to the computer takes longer time. Now mesh adaptivity is another feature of fluidity, which is very useful, and we'll be using it tomorrow. I'll quickly browse through it. The whole idea is that the solution by its nature can be changing in different ways in different points in space. It could be the case that in one point in space, the solution is not changing at all. In the other point in space, it's changing drastically with time. So our mesh nodes can be made non-homogeneous, and the mesh can evolve in time. It could also happen like for example, in boundary layers. The gradients are very strong in one direction, but they don't change much in the other direction. So we can have these elements which are elongated, anisotropic meshes or elements can be created. So we can use these ideas and very effectively solve equations. Let me show you some solutions of the bubble column problem that we'll be briefly touching upon tomorrow. So as I said that we need some functions, we need kernels. So for example, breakage is there. So breakage depends on turbulence. It also depends on a balance between surface tension and viscosity. Viscosity is trying to shear the layers, break a bubble, whereas surface tension is trying to hold the surface, so save the bubble from breaking. So all the physics comes into these physical closures of breakage and coalescence. So we have to choose those models. And when we do that, what you see in this figure is on the top, you see Sauter mean diameter. So we can see that the diameter can be tracked, and we can also track correctly now, or more accurately, the air volume fraction. So you can see that there's a plume that oscillates and then gets steady. This is a comparison of liquid velocities that we predict versus some experiments. Experimental data was available. We can see there's a decent match. Here we see gas holdup, which is again gas volume fraction. So we see a very nice fit with experiments here for these polydisperse flow simulations. So this was a brief introduction to the solutions. We'll talk more about it in later sessions. Now talking about fluidity code, why are we using fluidity? Why are we using FEM in general? Now strictly speaking, finite volume method is a special case of finite element method. Okay. If you take 0th order polynomials, then you get finite volume method. So mathematically speaking, finite volumes is a special case of finite element. Now finite volume, what happens is, the way we implement it, we have to find flux terms. If you have used it, you will see that if you want more accuracy, you need, or if you change discretizations, you need different discretization for flux terms. So finding those flux discretizations can be very challenging and very particular to a given problem. But in FEM, it is very natural. With higher accuracy, you go from linear to quadratic, quadratic to cubic. Okay, then you can increase accuracy. So FEM in general, it takes mathematically, it's more demanding. If you want to implement it computationally, it takes more time. That's accepted fact. But if you have been able to implement it, then if it's available to you, then it can be more effective. We use a parallelized version. So what happens is you can use multiple cores of a computer to solve it. So typically nowadays you'll have 4 to 8 cores in a machine. So you can utilize those for solving problems. Just a second. The other reason we use this because fluidity allows us to use Python scripting. So we don't need to change the code every time and compile it. We can implement simple Python scripts. If you want to implement some arbitrary shape initial condition or arbitrary boundary condition, we can do that through Python scripting. We can implement both univariate and bivariate. Bivariate population balance is also available, although our discussion will be mostly around monovariate, but that feature is available. And we have shown the accuracy through the results I just showed you. So there are multiple ways to install fluidity. It works very well for Linux-based systems. But to avoid that, what I've done is I've created a virtual machine, which is can easily be opened in VirtualBox software. So all you have to do is, if you have a Windows or a Linux machine, you download VirtualBox software. You download the virtual image from this link. It's a LXD based Ubuntu virtual image. It has all the software installed, or everything installed in it. So once you open it, you can log into the virtual machine using this username and password, and you can try it. At least try to log it first, and then after that, we will discuss things further. So let's close this session. I've talked about a summary. I'll talk about it further. So that was all for today's session. Do we have any questions before we close? Are the people still available online? I was using my phone internet. I think we lost connection there. Am I still connected?
Yes, sir.
Yes. Okay. Well, now I lost it. You are still connected there? Are you connected to this meeting? Can you give it to me? I've lost my connection here. You can do that? Okay, please.
Use this password.
Just a second.
SBRA. That's it.
I'm sorry for that. I got disconnected. Do we have any questions? Yeah, Govind, please.
Sir, I just want to ask about the condition of the mesh convergence in the dispersed phase, that how we are going to check the mesh convergence.
Okay, so mesh convergence in the population
Yes.
balance equation, right? Right. So population balance equation, what we are doing is we are solving for the weights and abscissas in our present method. Now, when we do a mesh convergence, we see one way is to see that the variable stops changing as you refine the mesh further. Now, these weights and abscissa fields, W alphas and xi alphas, are what we are solving as a function of x and t. So what we can do is we can take the mesh size, let's say number of mesh nodes, and then you can take one of the, let's say W1, and you can see that as you increase the number of nodes, you will see ultimately it should settle down and then become flat. So that's how we. It's a mathematical idea. There's no link with the physics here. So mesh convergence is a very mathematical thing. So we are solving for scalar equations. So we check for the convergence of scalars.
Sir, as W alpha is changing with space and time also, so here we are plotting W1 with respect to nodes. But if we
Yeah, so W1, good point. W1 as a function of for a given x position and for a given time. That is what you do typically in any other case. For example, if you're solving for velocity, then when you do mesh convergence, you check for the velocity at a given point at a given time. When you compare that number of points.
Okay, sir. Thank you, sir.
Any other questions? Yes, Hussain Bacha.
Sir, you explain about FEM or FVM. Now I want to ask that if the time dependent step is taken, means you have shown the example of stationary part. If the time dependent term is there, then sir, how in FEM we can do such analysis of time steps?
Right. So let me go back to that. So the last equation that we have on this slide is precisely that. So dc by dt denotes the derivative of the coefficient c as a function of time. And we are trying to find coefficient c. So we use some sort of a theta scheme here. So we write d by dt of c, let's say one of those, c1, as c1 new minus c1 old upon delta t. Okay, so that's a forward time difference. We can do a backward difference. We can also do a theta amount of this and a 1 minus theta amount of this. So that gives us something like a Crank-Nicholson scheme if theta is half. So there are multiple schemes possible out of this. So ultimately, when you have decided what your theta is, then you get this equation in terms of vectors. So finally, you will have some matrix times C is equal to some known vector. So all
So
these
Ax
matrices
equal
are
to
known.
B, right?
M is known, A is known, K is known, and this M is also known, and this S is also known.
Sir, at last, one more question I want to ask. Sir, at last you have shown the volume fraction graph of as an output. So, sir, this graph are on average basis, maximum basis, or minimum basis, or if we want to draw, how we can draw that type of things?
I have shown you the gas holdup, right? This one.
Yes, sir. Yes, sir.
So
This
this
type of graph
gas holdup is averaged in the whole volume, complete volume.
Okay, sir. Average basis it was drawn, sir.
Yes,
Okay,
yes.
sir.
So gas holdup basically means that what is the amount of gas in the overall volume that you have here. Okay, so that's the integral of the volume fraction of gas.
Okay, sir. Thank you.
Any other questions? This one. So this is experiment and this is simulation. So we are qualitatively trying to show you what is the plume behavior that we have here. It's an oscillating plume. So we are trying to show you that for lower superficial gas velocities or flow rates of gas, you see a very lean, but as you increase the flow rate, you see a lot of mixing that you're seeing here. So mixing increases as you increase the flow rate. Turbulence increases. It's a qualitative comparison. And don't expect qualitatively things to match. If they are matching, then there is a significant amount of control you have carried out on these figures. I mean, they will not exactly show you it's an oscillating plume anyways. Many assumptions are there. Right. So thank you very much. We will close this session now. And the next session we have is at 4:30 p.m. today. And definitely I request you to attend that. It's going to be very interesting. Pablo, who has a lot of experience in applying these models to real world phenomena, he will talk to you about how these equations and how in general modeling is carried out for minerals processing applications. So so this was mathematics part. If you go through that, it will give you a lot of motivation as to how to model things and implement them. And where is what part valid and where is what part can be neglected. Okay, so I'll see you at 4:30 p.m. today, and all the best. If there's any question, you can always email me at gaurav@itmandi.ac.in. These slides will be uploaded on the website that was shared with you. Thank you very much.